Now let's see how this matrix factorization technique are useful for the collaborative filtering. Let's see. So the matrix, the recommender matrix that we got in our first lectures of this series. So this is a one kind of sparse matrix. So this is A, let A. This is a sparse matrix, and this is a rectangular type matrix, and the columns are denoted by the individual users, and the rows are denoted by the individual users, and the column are denoted by the individual corresponding to individual item. Okay, and these are the given rating or watch history, or it is the some history, some kind of rating that have been given by the users of a corresponding product. If it is a movie, so how much times he have movies. If it is product, how much time he have search on this product. And okay, such kind of ratings, such kind of things are denoted by aij. So the first characteristics for this matrix A is aij. Aij are the rating of aijs are here, the rating or simple some data, user based data. Actually, just take the example, movie examples for better understanding, for better discussions. Let's take A is the recommender matrix that's come from the Netflix data. Okay, so AI is the rating on the item or on the movie ij by the user's UI. Okay, that's the thing. Now the second characteristics of this matrix is must be a sparse matrix. Okay, because most of the values of this matrix is empty, because it's not possible for a single user to watch all the movies or to to find all the item. Okay, it's totally a irrelevant thing. So for these reasons, it's a sparse kind of matrix. It's a sparse matrix. Okay, so means the many empty cells they have. Most of the cells are empty. Here most of the cells are empty. That's the first reasons for this is collaborative, for this recommender matrix actually. Okay, that's the first reason. Now the in just in previous lecture we have seen the NFC means a non-negative, NMF, non-negative matrix factorizations. We have seen this concept. Now let's try to apply this concept on this factorizations, on this collaborative filtering. How we'll apply this thing? So in non-matrix factorizations, we have a matrix A. Now we have to factorize the matrix in such a way that B into C transpose. It's called the NMF, non-negative matrix factorizations, where B and C is a non-negative matrix. All the element B and C are greater than 0. That's the conditions here. We got it. So suppose let's take the dimension there have. Suppose let the dimension there have the dimension of the matrix A is let M cross N cross M. Let this dimension is this. This N is responsible for number of users. This M is responsible for number of users. Okay, and this AM is responsible for number of items. Okay, now let's compare to it. So what will be the dimension of B and C? So the dimension of B will be N cross. So if since it is a N cross M matrix, the dimension will be N cross D. Suppose let's sum D, and the dimension of the C dashed. The dimension of the C dashed will be what? D cross N. Okay, if this dimensional, if we found this dimensional, there's only it's possible to after multiplying these we got this value. Okay, this is possible. So the B here, is what? B value is N cross D. And the C is what? C value is transformations is actually, I think I've did some, it will be M, sorry for that. So its transformation is D cross N. So C, the dimension of the C will be, so M cross D, this value will be that. Okay, you can treat these things. Now let's try to understand it significantly, why this actually, how these things are actually useful in this recommendation system. So let B is equals to N cross D. Its dimension is N cross D, means it has n rows. If you treat, you can think it's like, look like this. You can think this is for user 1, user 2, like it's for user n, and for each user, for let's take it's then random arbitrary user ui, n users, and for each user they are have the corresponding features vector, d-dimensional features vector for this user I. These are the d-dimensional features vector for this user I. You can consider these things. You can consider this B matrix is like that, and similarly also you can consider C matrix like that. The dimension of the C is M cross D. M cross D is dimensional is M cross D. So for that reasons we can write in these things as a I1, I2 up to item M, IM. Okay, and let's, if is a common element, if we take IJ, so we can write these things like in this scenarios. You can like, so this you can consider these things as a d-dimensional item vector. It's a d-dimensional user vector. You can consider like, it will be better if you write item means it's I features vector for each item, feature vector for each item. And these things you can consider features vector for each user. You can consider these things as a these things as a features vector for each user. You can consider this thing like that. Okay, this is the, now let's, what is D actually? So the D must be greater than 0. The D value of the D, it must be greater than 0, and the B value is less than equals to minimum of, it's the D dimensional, it's minimum of M and N. Means what? Means that means D is less than is equals to M, and also D is less than is equals to N. That's the thing actually, the reason, the meaning of D is here, like it's the a smaller value, that a smaller minimum value of M and N. That's the means, and it's the dimension of the its users, and as well it's for each item, it's the features dimension. You can treat this D as like that. Okay, I think you got the idea how these matrix are actually, matrix factorizations are useful in this collaborative filtering. Now let's discuss the internal mathematics, how we will use this. So to compare this matrix side by side, I think it will be more visualizable. So here we have taken, suppose let's take, it is the A matrix. This is the A matrix. Let's take it's our A matrix, and its dimension is what? The dimension is M cross N cross M, and suppose let it's the B matrix, and it is the B matrix, and another one is C transpose matrix, C transpose. This is the C transpose matrix actually. So the transpose of B is n cross D. Dimension of the B is a dimension of the C transpose is D cross M. This is the dimension. Now let's take any element here. How to find this element? So if you write these things, we can write these things as like that. It's for U1, U2, for any element Ui up to Un. These things can be written as A1, I2, like any element Ij, Im. Similarly for here, it is for this Ui. If we just consider this thing, if you just consider this is a Aij. Now this element can be and we can found this element like that here. So this is Ui, this is responsible for Ui, this features vector. This is the features vector of the edge users. These are the features, d-dimensional features vector of the edge users, because we have d-dimensional column, and it's the C transpose. We have seen that it's look like this is the for each items. If we consider I1, I2, somewhere here it will be Ij up to Im. So this value will be d-dimensional. This value is the d-dimensional features vector for each item. This value is actually d-dimensional features vector for each item. Now if we multiply these two things, if I multiply Ui, means I am talking, it's better if I talking these things as a B for this B, for this B matrix, if I call these things as a Bi transpose, means for column vector, for B element, for B matrix, the column vector for B matrix is Bi. Bi is the column vector for B matrix, and this is the column vector for the C transpose, actually C transpose. So you can treat these things for this matrix, you can call this as a Ci. So what is the dimensional? So first I think it will be better if we write these things in this way, in this format. So AI, the dimension of the AI is what? 1 cross 1. That is the singular value, scalar value. Actually, this one is. I have to produce this scalar value. Actually, here how much row have? This is the UI corresponding. That is the UI corresponding features vector of the UI. This one. And this is the corresponding column vector for the UI for the item J. So its dimension, if you just think this is dimension single row D column 1 cross D. Its dimension is D column single row. So these things, if you multiply these things, we got a 1 cross 1 matrix. 1 cross 1 matrix. Okay. So this is actually a column vector. This is actually a column vector. So these things are the ith row of the matrix B. See these things. Now write these things. These are the ith row of B, and these things are the jth column of C transpose. Means what? Jth column of the C transpose of means jth row of C. These things are the, we can in general, we can jth column, jth row of the matrix C. It is the jth column of the matrix C transpose, that means it's the, sorry, jth, it will be jth column, jth row, sorry, it's the jth row of the matrix C. Okay, that's the thing. So if you just write this thing, ith row of B, if we just write the ith, if you write the bi, if we take these conditions, if bi is the ith column of the matrix B, and if Cj is the jth column of the matrix C, okay, then we can write this, then we can write this matrix is like this way. So we have treat bi is the ith column of B, so it is the ith row of B, so we can write these things as a bi transpose. It is the, this is the ith row of B, and bi is the ith column of the B. If we convert this column into row, so it will be bi transpose. And if Cj is the jth column of C, if Cj is the jth column of C, so these things are the jth row of C. These things are the jth, this thing is jth row of the C. So these things will be simple. These things will be simple. The C, I think I have. Okay. Sorry for that. It's suppose let's is the, it is the, let it is the bi is the bth row. I think it will be better, for I have denoted here B by simple the, this is user, we have represented the row vector, and for C also this row vector is represent the S item. Instead of using the column vector, it will be better if we using the row vector here. It's better, it will be better. It will be better if we using the row of ith row of B, and it is the ith row of C. Cj is the, okay, this is actually, this bij actually for user I, this responsible for the user I, and this Cj is actually responsible for the item J. It will be better for us. So now if it is the bi is the ith row of B, so now this vector will be, remove this thing, now this vector will be this ith row of it, so this vector will be bi ith row, and jth row of C, and it is the jth row of C, and jth row of C, and Cj here we have taken here, that is the column vector. Actually this is the column vector, so by simple we have to use the Cj transpose. Actually a is what, A is actually B into C transpose. Okay, and these things are the column vector, it is the row representation is the column representation. So because of that we have to use this Cj transformation. Okay, I think you got the idea. So at the, if we finalized aij, we can write aij as the bi into Cj transpose. So here bi is the ith row, which bi is for responsible for each user, and Cj is responsible for each item. Okay, and this value are actually sparse, for a sparse matrix this value is empty. For a sparse matrix, most of the values of this are the empty value, most of the value. Now our job is to, we have to predict this value, we have to predict for a empty cells, we have to predict, that's our actually job. So our main job is, so let's try to, our task is here now, our task is for the aij that is in empty cells, using these formulations bi into Cj transpose, we have to predict this empty cell, to predict these empty cells. Okay, have to predict the empty cell. That's the main job we have to do here. Okay, so by using these matrix factorizations, what matrix we have in, we have the matrix A is equals to B into C transpose. We have this matrix. Because of these reasons we have transposition. If we combine all the things, then we got this matrix actually. So we will use the optimization problem. Some optimizations problem we will use. It will be gradient descent. Any optimizations problem we can use. In optimization chapter, solving the optimization problem chapters, we will see how to solve the optimization problem by simple any technique. We can optimize. We can easily optimize these things. Some optimization algorithms. It may be gradient GCD, gradient descent algorithm, something. Most of the time we have used stochastic gradient descent. It is a very easy to optimize any problem. Okay, most of the time we will use this stochastic gradient descent. Now let's see how to formulate how to the mathematical optimizations functions to find the B and C. So our main task is to predict this value. To predict this value, we have to find what is the value of B and C. That's the main job here. How to predict this, how to find this B and C. So now let's see how to formulate the objective functions. The task is how to find. The task is how to find B and C. That's the task here. How to find these Bx. So if we find this B and C, then this task is okay. Then we can easily this matrix A as a factor matrix factorization. But so by we apply the simple the matrix factorizations concept here. This constraint we will apply. This constraint we will apply to find it. So let's see how to find. So we have to find the argument arc mean over B. We have to find this over B and C. Actually, at the end of the day, we have to find a B and C. So how we'll find this? We have to find by using this formula Aij minus this one. If this is equal, that means what? That's everything is okay. Everything is correct. Using Bi into Cj's transformation, Bi into Cj's transformations. We will have to use these functions, and it must be over all Ij. It must be over all Ij. All Ij means we have to consider those Aij that have only non-empty values. So for an empty values, how to find this? How to compare these things? How to compare this argument value? So we have to consider those Ij's such that here the constant has occurred such that Aij is not empty. Is not empty. That's the constant we have to use. That is actually it's also must be a square value. Just let it. You have to find this differences and square value. Okay, differences square value, and where this is the constant part actually. If you this is the objective functions. These things are actually called the objective functions. And these things are the constant of this objective function. Constant. Okay, we have to consider those Aij value where only here non-empty cells. So if we have the non-empty cells, then we can use this value and find the difference. If this difference is actually properly 0, if suppose we got this B and B value, suppose let Ai minus Bicj, it is we got this 0, means everything is okay. Our predicted value Bi at the end of the day, you have to find the B and C. If we got such B and C that it give the output 0, then it's okay, no problem. But we have to find the minimum value. Okay, those no non-empty cells. For the empty cells, we have to predict this value. For the empty cells, which Bi and Cj are responsible, we have to find these values Bi and Cj. That's the main job here we have to do. Okay, that you can think these things as like a square laws. Already we have seen in logistic regression chapter they have square laws, hinge laws, various type of means logarithmic laws, or there are various type of laws we have seen in the regression and classification chapter. But this thing, you can treat these things square laws term. These things as a squared laws term. You can think these things. Okay, and the BC here is we have to predict the BC. It must be a matrices. It must be a matrices. Okay. So the first constant is Aij, that we have not considered in our calculations, that those are the empty cells. Only fewer, because we have seen A is a matrix that we have considered. The recommender matrix is a sparse matrix, means most of the cells are empty. We have to consider those cells only. Only those are the non-empty cells. In our calculations, we have to consider only non-empty cells. Okay, these are the constant over here. Okay, these things we can easily solve. We have seen already these problems can be easily solved by the GCD, stochastic gradient descent. It can be easily solved. It can be solved by stochastic gradient descent algorithm. We have seen in the chapter of the optimization solutions of the optimization functions, mathematical optimization. We have seen these things, how to use the stochastic gradient descent. Okay, that's the solve the problem that we have to after solving. Suppose let's take we have used this technique, we have find. So first we have to generate this is the step, this is the first step that we have to do. In first step we have to generate this optimization problem, and using by simple the gradient descent algorithm, stochastic gradient descent algorithm, so we can easily we have solved and find the value of B and C. The second step that we have to do, so by after solving this, solving the optimization problem, after solving the optimization problem, let so we got this matrix B and C, we got it. So B is for responsible for each user, just see it. B is responsible for each user and C is responsible for each item. So the row vector of B will be, the row vector of A will be U1, U2, somewhere it will be Uj, and up to Un. And this row vector will be responsible for each item I1, I2, somewhere it will be Ij, and Im. Okay, so these things, and the dimension of that matrix is n cross d, and this dimension will be m cross d. Okay, these are the things. So this we have called that the, sorry, it's the J, I think it's it's my bad, ui, it's, and the ith row of B is the bi, means these J, these things are actually the bi. These things are actually bi, and the J is the jth row of the C, and these things are actually the Cj's. These things are actually the Cj's. Okay, so here n is the number of users, and m is the number of items. So after solving this, we got this vector, means the features vector for each users and the features vector for each items. We can easily got by solving this optimization problem. This is the second step. So So first step, we have to solve the optimization problem by using the valid it aij, means non-empty aij, non-empty, or you can call these things as a valid aij or a valid aij. These are the constant here. And second step, after solving this, we have to find the features vector for each users and for each items. We can find it. This is the second step. And the third step that we have to do here, the third step, suppose we have to predict the value for the non-empty cells. Suppose let this is our original A matrix. This is the original A matrix that we have built from our original data set. Is the recommender matrix. That's the original matrix we have. And after finding the after calculating the optimization problem, we have to predict this matrix, recommender matrix. Okay, how we will predict these things. Suppose these things are responsible for each row is responsible for each user. Somewhere it is UI, somewhere it is UN, and each column is responsible for each item. Somewhere it is IJ, item M. Okay, suppose let some more, means let's few of them are non-empty. Suppose let's this blue color are the non-empty cells. It is the non-empty. Let some few of them are non-empty. Non-empty here, non-empty here, like that. Suppose let the rest of the items are the for null matrix. Suppose I am using here the red color for the empty values. These are the empty values. These are the empty values. It's most of the values are the empty. Sparse matrix, actually it is a sparse matrix. Most of the values are empty. This is the empty cell. These are the empty cells. Okay, now our job is we have to predict, our task is we have to predict these empty values. Our task is here, our task is that we have to do after finding this B and C. Task is predict, to predict these empty cells. We have to predict this job. Okay, so how to predict? Suppose let's for simplicity, let's take an empty cell. Suppose I am picked up this empty cell, and let's take this empty cell dimension is f10 f10 5. Let f10 5 is an empty cell. We have to predict it. Let f10 5 is an empty cell. Empty cell, we have to predict. We have to predict it by using B and C. By using B and C. That's the job that we have to do. So how we'll do that? So in the B matrix, if you see B and C matrix, we have already calculated from by solving this optimization problem. By solving this optimization problem, we have already calculated the B and C, and we have solved. How we will solve these things? By we have solved this optimization problem by using the non-empty values, means by simple using the valid values of the aij. Those cells have the valid value. Only we have this data to predict these non-empty cells. So this B and C, the each row of the B and C must be a non-empty values, non-empty rows. Okay, since we have used the non-empty elements of our AIJs. Okay, that's why we have considered only the valid items, valid values of AIJ. Because of these reasons, each row must be a non-zero row. Okay, so for these reasons, we can to predict like this way. We can predict, since since B and C are have non-zero, have non-zero rows, non-zero rows, so we can easily predict A10 and 5 it will be, since A is what? A is the multiplications of A is what? A is multiplication of B and C transpose, and Aij is the simple multiplications of Bi and Cj transpose. So Bi and Cj transpose. So we can B10 into C5 transpose. If we multiply these things B10 into C5 transpose, then we can easily calculate it, this A10 5 value. Okay, and since this is the non-zero, so this value will be, must be a non-zero value, must be a non-zero value. Okay, so we call these things as a hat, we call these things as a hat. Okay, this is called the predicted value, these things are called the predicted value of A10 5 by doing this simple matrix multiplication, vector multiplications. We can easily doing this job. Okay, that's the job that we have to do here, finding my empty shells in A. That's the job. This is the predicted value of Aij, and it's not equals to empty. Okay, I think you got the idea how to predict this thing, how to predict this value. So in third step, this is the most important step. So let's recap the third step again to for more clarified the idea. Let's, so at first we got, this is the A matrix, this is the recommender matrix that we have collected from the user. The most of the elements, this is a sparse matrix actually. This is a sparse matrix. In the most are empty, means most of the elements are empty here. Most of the elements are empty here. Okay, these are the most of the element. So our job is, after building this, after set up this optimization problem by using the some optimization technique, we have to calculate this B and C. Okay, after calculating this B and C, our job is to predict, suppose let's say it's the predicted A, this is the original matrix A, predict this value by sample using this B into C transpose. By using this multiplication, matrix multiplications, we have to predict it. It's a sample. This is the computed, this value will be computed by using the Aij that are non-empty by solving the optimization problem. Okay, that's the job that we have doing here. We have to compute it. We have to compute it by using Aij's that are non-empty by solving the optimization problem. By solving the optimization problem, we have to doing. So it is a sparse matrix, but the AI hat that we have computed, it's a non-empty cell. Most of the cells are non-empty, but in this case, most of the cells are here are non-empty. So because we have used this optimization problem, on this optimization problem we has a valid AI. Okay, so because of this most of the cells are non-empty. These are the simple predicted value. These are the, so now the term is here A, and the difference with A and A hat, the differences of A and A hat will be very small. That's the thing, very small. Okay, so now I have to compare these things side by side to predict it. So suppose let now how to give the output, let's see it. So let this is our original matrix A. Now we have to compare it to the matrix A hat. Let the green one is the A hat, this one is the A hat. This is the predicted, this is the predicted matrix. This is the predicted and this is the original one. This is the original one. Okay, by solving this optimization problem. So in this matrix most of the cells are empty. In this matrix if we see most of the cells are empty cell, means few are the non-empty. Suppose let these are the non-empty cells, some few of them are the non-empty, few of them are the non-empty cells. Okay, rest of the empty cells. So now using this data and here and in this matrix, but in this matrix most of the elements are a valid number, most of the cells are non-empty. Most of the cell are non-empty, but here most of the cells are empty. Now suppose let we have to find some empty value, we have to predict it some empty value. How will predict this thing? So we have to predict it some. Suppose let it's the user I, this where somewhere here user I, had somewhere here item j for this matrix. Similarly also there have some user I, somewhere here user j. So corresponding some value, suppose let for this matrix some value here, this is the empty cell. Somewhere here empty, somewhere here empty value, it is empty value. Now we have to predict this. How to? Now somewhere here also we can find this, how much value it will have, how much value. So now if we have find this predicted value, we have to pick up. So these value are actually, so the value a I j, these are the call, actually these things are the actually a I j at, okay, these things, this a I j hat are the predicted value of this empty cell. These are the predicted value of user I corresponding to the item j. Okay, these are the predicted value. Now based on this predicted value we can recommend it something. This is a very high values, then we will recommended it, otherwise we will not recommend it. That's the thing that we have to job. So that's getting, this is the predicted value or predicted rating we can call it for the item, predicted rating or predicted value for this item I, for this item j corresponding to the user. So this is the job that we have to do here. This is the job. So So what we will see actually in this lecture, we will connect this matrix factorizations. We will connect these matrix factorizations to building a collaborative filtering recommendation system. To build a collaborative filtering recommendation system. Okay, in previous lecture we have learned the concept of how to use this matrix factorizations concept to build a PCA principle, how to solve this using this matrix to compute the PCS algorithm. In next video we will see how to use this matrix factorizations technique to features engineering. Okay, and after that we will see how to use this matrix factorization technique for clustering technique. We'll see these things. I think you got the idea how we will use this matrix factorization technique to build simple the collaborative recommendation system. Okay, just recap these things. So first, the thing that we have to do, we have to define the optimization first. Optimization problem. How we'll define the tasks that we have to do. We have to predict the empty values for this recommender matrix. If we somehow predict these empty values, then we can use this we can predict values as rating or as some recommendations using this. Okay, actually this AIJ are the rating of the item J and involved by the user's UI. And since we have seen that in these cases most of the value are empties. Okay, somehow we have to predict these empty cells. So if we predict these empty cells, then we can easily build a recommender system. So the task is here, we have to predict this empty cell. And how will predict? The only data that we have, only few are the data that we have that are the non-empty. Okay, means others rest of the empty on this matrix. So by using these non-empty values, we have to predict it. So just we have to first we have to build this optimizations problem. We will see in depth how to build this optimization problem by simple building this optimization problem, and in general we have used the gradient stochastic descent algorithms to solve this optimization problem. So after solving this optimizations problem, and we have to we have to find this matrix B and C. So here we will solve this optimizations problem by using the constant that's Aij, that's the known empty, means valid Aij, that's actually our constant here of this optimization problem. And after solving this optimization problem, we by using this B and C that we have got by solving this optimization problem, the B is responsible for the features vector for each users, and this C matrix is responsible for the features vector for each item. Okay, and these are the matrix B and C that we have predicted. That's most of the elements are non-zero. By simple the multiplications, in third step we have to doing the simple multiplications of B and C transpose. We got the predicted value of Aij, and based on this predicted value of Aij, we have to build the recommender system. Okay, I think you got the idea. This is a simple idea that we have to use. This is the simple matrix factorizations idea that we have used here to build this collaborative filtering technique. I think from these large discussions, it is clear all of you. Although if you have any problem, please comment below, or please I request you please revisit this lecture video again. Okay, and after revisit it, if you have any problem, please comment below.